All right, let's continue with examples of dot product. Okay, now we know that a vector A is perpendicular to a vector B if only if the dot product between them is 0. Okay, for instance, we do this example. Suppose we have a unit circle. Let's plot a unit circle. Okay, so we have a unit circle. Now, suppose the center is O. Now we have x-axis. Now suppose any point. Let's take any point. So suppose this point is A, center is O, and this point is B. Now any point on the circle, suppose is C. Now we actually, from geometry, we know if we connect AC with BC, AC with BC, then this we get actually 90 degree. So we actually, if we don't know this theorem, then we actually prove that we want AC is perpendicular to BC. We want to prove this using coordinate dot product. Now this is the unit circle, so we can write the coordinate of A and B. A, the point A, this is 1. This point is 1. Unit length, unit radius. So this A is, we can write down, A is 0, 1. B is, so suppose this X is the Y. This is the Y axis. Okay. Now suppose this angle is theta. Okay, so we can write down. We can write down the coordinate of C. What's the coordinate of C? Coordinate of C we can write down as the x coordinate is cosine. The y value is sine theta. Okay, you solve the triangle. Okay, unit length. Then you find the height of C is sine theta, and then the x coordinate is cosine theta. Okay, so this is cosine theta, and then this height the height is, this is sine theta. Okay, then we can write down the vector AC and BC. Okay, so B here, A is 0, 1, B is -1, 0. And then AC, C, we have the coordinate of C. So we can write down the vector AC. Now it's head minus tail. So it's cosine theta, x coordinate of C minus x coordinate of A, 1. Now sine theta minus 0. Just sine theta. Okay. Then BC, vector BC. You see, this is a x coordinate of C minus x coordinate of a B. So we get a cosine theta minus 1. So it's plus 1. Sine theta again minus 0. We again get a sine theta. So use dot product. Then AC dot product with BC. Remember dot product. So we multiply x coordinate with x coordinate, y coordinate with y coordinate, and then add the component.
I have a
question? Any questions?
Professor, I have a question, please. Yeah.
Okay. Any?
The head and what's the tail?
Any? Can you see it loud about the question?
Yeah, in the circle, you decide the head and tail. Where is the head and where is the tail?
Head and tail. Head and tail. Okay,
Head
so
and
if you
tail.
write AC,
Yeah,
you see it's head and tail. So suppose you have vector. This vector A from B. Okay, so this is the head. This is the tail. Okay, if you write AB, The right side letter is tail. Sorry, the right side is tail. The left side is, the right side is B, here is head, A is tail. Yeah. Does that make sense?
Yes, thank you, Professor.
Okay. So you see the vector AC. So the C. So we start from A and at C. So C is the head. Okay. So you see the arrow pointing towards to C. C is head. A is the tail of the arrow. Okay. So you see, I think the dot product that we define in the coordinate form. Okay. So suppose, you know, remember x, let's see, x1, x2 times y1 and y2. Then this we get x1 times y1 plus x2 times y2. Okay. Then, so we x first times the first coordinate. So it's cosine theta minus 1 multiplied cosine theta plus 1. And then plus the second coordinate multiply the second coordinate, sine theta times sine theta. So then you distribute. So use difference of two perfect square, difference of two perfect squares. You get cosine squared minus 1 squared, and then plus sine squared. And then we know sine squared plus cosine squared is 1. So cosine squared plus sine squared minus 1. Now cosine squared plus sine squared is 1, so it's 1 minus 1, which we get a 0. Okay, so you see the dot product is 0. Dot product is 0, then we can get, the two line segments are perpendicular. AC is perpendicular to BC. Now this is the famous Euler theorem from geometry. This is well known in high school geometry. Okay, this paper is from this time. You see, so it's really old, really old. Okay, use vectors we can do a lot. For instance, we can do trigonometry. For instance, suppose we have two unit vectors. Now let me insert a circle. Okay, suppose we have a unit circle. This is the unit circle. Now, maybe I made. Okay, suppose this is the unit circle. With center O, this is x-axis. Now this is y-axis. Center is O. Now suppose we have two unit vectors. Unit vector v1. This is unit v1. And then we have another vector v2. Now suppose this angle is alpha, and then the angle corresponding to v2 is beta. Now, first question, what's the angle between v1 and v2? What's the angle between v1 and v2?
Beta minus alpha.
Beta minus alpha, correct. So the angle between v1 and v2 is beta minus alpha. Okay. Now unit vector. So this is the unit circle, which implies the radius is 1. Radius equals 1. So this means the magnitude of v1 equal to magnitude of v2 is 1. Okay. So we can get, by definition, v1 dot product with v2. By definition of a dot product, we may get this norm of V1 times norm of V2 times the cosine value of the angle between them, beta minus alpha. Okay. Now this is actually 1 times cosine beta minus alpha. So this is nothing else. It's just cosine beta minus alpha. Okay. On the other hand, we can use coordinate. Okay. Use coordinate to do the dot product. Okay. So write down the coordinate of V1. What's the coordinate of V? Coordinate. Let's see this. Let's see OA. This point. Let's use A. This point we use B. Okay. So the head of V1 is OA. Okay. This is OA. Now you can write down the coordinate of A. Coordinate of A. This you solve geometry. You solve this geometry. You find the coordinate of A. Okay. A. The unit. The hypotenuse is 1. So you can find the two sides. So you can find A. You can find A, which is the coordinate of A. You can find it very easy. So it's A. Let me write here. A is cosine alpha, sine alpha. Okay. Similarly, you can work out the coordinate of B. Okay. B. Solve the geometry. Solve the triangle, right triangle. So the height of B is the height. The y value is sine beta. X value is cosine beta. Okay. So once we write down the coordinate of A and B, so we can write down the vector form. Okay. Now O is of course 0, 0. So A is cosine alpha, sine alpha. So we subtract head minus tail. Excuse me. And then we can find the vector in coordinate form. This we get cosine alpha, sine alpha. Similarly, V2 is OB. Now B, you can find it cosine beta, sine beta. Okay, so you get this is head minus tail. O is of course 0, 0. O is 0, 0. X, Y, they are both 0. So head minus tail, the coordinate of B, subtract the coordinate of O. Then we get cosine beta, sine beta. So you see V1 times V2, dot product with V2. Now, according the coordinate form of dot product, then we get X times X plus Y times Y. Okay, the first component multiply the first component. So we get the first component cosine alpha multiply the other first component cosine beta plus the second component. We get sine alpha times sine beta. Okay. So we have another way, we have two ways to compute the same quantity. So we should know that these two quantities should be the same thing. So we get cosine, so this implies cosine beta minus alpha, which should be cosine alpha, cosine beta. Okay. And then we should get sine alpha, sine beta. Okay. Now, for instance, if you replace alpha by negative alpha, so we get addition formula. So alpha, if you replace alpha by negative alpha, then you get a cosine alpha plus beta.
Yeah, I wasn't sure if it had died because I called back a couple of times and it went to voicemail. So I thought maybe your phone had died or something.
Oh yeah, okay. Well, then when I try to call back, I forgot you got a dial.
Okay. So replace alpha by negative alpha, then we get, cosine is even function. So this cosine doesn't change. But sine alpha, we should get sine negative alpha. Sine is odd, so we can get a negative sine alpha, sine beta. Okay, so we get addition formula for trig. Addition formula for trig. Cosine value, okay, cosine value. Of course, you can use the inducer formula. So sine, you see sine alpha plus beta, which is cosine pi over 2 minus alpha plus beta. And then you use this again. So you get use addition or subtraction. So you get a cosine. So that's very easy. So suppose you write this as cosine pi over 2 minus alpha minus beta. So this you get, use the addition formula. You write anything as a thing. So you get a cosine pi over 2 minus alpha cosine beta plus sine pi over 2 minus alpha sine beta. Okay, so you get this cosine, you use the induced formula again. So you get this sine alpha cosine beta plus cosine alpha sine beta. Okay, so you get addition law for sine function. And then if you let take alpha equal to beta, then you get we get a sine twice alpha. Then you get you let alpha equal to beta. Then you get actually sine alpha cosine beta. Then this actually you get the two terms are the same, sine alpha cosine alpha. So you get the double angle formula. Okay, double angle formula. And then similarly cosine 2 alpha. Then you get plug in, let alpha equal to beta. Let alpha equal to beta. So this you get cosine alpha times cosine beta. Cosine beta is again is the same thing as cosine alpha. So you get this is cosine squared minus sine squared. Okay, etc. etc. So you get a double angle formula and addition formula for Chig. Okay, maybe another example in geometry. Okay, this example, the parallelogram law. The parallelogram law. Okay, prove this by geometry. So suppose we have parallelogram. Now let me just insert the parallelogram. Let's just insert the parallelogram. Okay, suppose we have parallelogram. So this is A, this is B, C, D. So for this parallelogram, show that AC squared plus BD squared. So the squares, the sum of the squares of diagonals of a parallelogram equal to twice AB squared plus AD squared. AD squared. Okay. Okay, we prove this using vectors. Okay, so we have the parallelogram law for additions. Okay, for additions. So this is, you see, AC, the vector AC is AB plus BC. AB plus BC. AB plus BC. Now, similarly, BD is the vector BA plus AD. BA plus AD. Now, let's simplify a little bit with our notation. Suppose let AB be, this is A. Now, BC is B, the vector B. Okay. So if you flip, so this is the AB vector, capital AB is A plus B. Okay, this BA and AB, they flip. So this will be negative A. Now AD is the same thing as B. Okay. So AC squared is AC dot AC. Okay, so this will be A plus B squared. So if you distribute this, so you get A squared. This let's use this. A dot A plus B dot B plus twice the cross terms. Here AB, their dot product is commutative. So we get the cross terms, twice A dot B. Now BD squared is BD dot BD. Dot product with a vector with itself. So we get its norm squared because the angle is 0. So you get this negative A plus B dot product with itself. Negative A plus B. So what you get is negative A dot negative A. Use distributive law. So you get a negative times negative, we get a positive. So it's A dot A plus B dot B plus minus actually minus twice A dot B. So you add them together. So AC squared plus BD squared. Add them together. Do you see? You get now you see we have a cancellation. We have A squared plus A squared. So the term are the same. The second term B squared plus B squared is the same. And then the last term 2AB and negative 2AB. You see they cancel each other. 2AB and negative 2AB they cancel each other. So cancel each other. Cancel each other. Cancel each other if we add them together. So if we add them together, then what's remaining is A squared dot A dot A. So we have twice that thing plus twice B dot B. Okay. Now dot product of vector with itself is its norm. Now if you factor out the 2, norm of A, you see norm of A, little a is just AB. Okay, norm of little a is the vector AB, the norm of AB. So this is AB squared. Now AB squared, you see B, the vector B is magnitude is BC or AD, they are the same, congruent. So this is the AB squared plus AD squared. Okay, then we are done. So we get the parallelogram law, parallelogram law for a parallelogram. So the sum of the squares of the two diagonals equal to twice the square sum of the two sides. Okay, so get the parallelogram law.
I have a question, Professor.
Question.
Yep. Up there, when you first split it into components X and Y.
Yes.
If you can scroll up a bit.
So you're asking about which one?
Here, yes. Here, when you made downward the parallelogram law, still.
Okay.
Yeah, can you scroll down a bit? I'll show you. Yeah, here. So when you wrote BA plus AD, which is equal to negative A plus B, I didn't understand this.
Aha! You see?
Yes.
Okay. So you see?
I got confused. Yeah.
BC and AD, you see, a vector is determined by its direction and magnitude. Okay. So you see, AD and BC, they are parallel. So which means they have the same direction. Okay. They have the same direction. BC and AD, they have the same direction, and they have the same magnitude. This comes from the property of the parallelogram. Okay. So this means this vector AD is exactly the same thing as B. Yeah, a vector you can translate it by parallel. Okay, parallel translated. So you again get the same vector because the direction does not change and the magnitude does not change. So which means you get the same vector. Remember, vector is determined by its magnitude and direction. As long as they have the same magnitude and same direction, they are same vector. Okay?
Okay, thank you.
So you see, if we switch capital AB, we switch the letter, two letters AB, capital A, capital B, then we flip the direction. Flip the direction. The magnitude doesn't change. If we flip the direction, we multiply it by -1. Okay, we flip the direction. 1 and -1, they are operate left and right. They are opposite direction. Okay. Any other questions? Any other questions about this example? Okay. Now let's go to next topic. Next topic. Next topic. Vector space. Vector space. Vector space. Now we define vectors. Okay, define vectors. What a vector is. Now the general idea in mathematics, one of the general thing is we do not study one object. Okay, if we want to study an object, we study all these kind of objects simultaneously. Okay, we study a collection of these objects simultaneously. I.e., we study similar objects all together simultaneously. For instance, we study, for instance, number theory. We study primes. Then we study primes simultaneously all together. And individual primes is not interesting, but how they distribute as a collection is actually more interesting. Okay. The idea like this: we understand a person by all its social relations. Okay, i.e., understand a person by all its relations with other people. Similar idea applies here. If we want to study vectors, we study all simultaneously all these vectors together, and this is all these vectors together. They form a space called vector space. So a vector space V is a collection of vectors such that we need to make sure when we do the natural operation of vectors that again we still lies again in this space. Okay, in this space, such that any linear combinations of vectors in V again lies in V. I.e., if we do addition or subtraction or scalar multiplication, this again is stable, lies in this space, such that any linear combinations of any vectors in V again lies again in V. I.e., a vector space is a smallest possible thing that is stable under operations of addition and subtraction and multiplication by scalars. Okay. So for example, one-dimensional vector space, suppose let U be the collection of vectors like this: xi, here x in any real number. So this just remember I, suppose I is this vector. X times I, we just multiply by x. Okay, if x is 2, we get a 2i. So then, so this is actually, this is 1, 2. So 2i is from 0 to 2, okay? So this corresponding to the x-axis, actually, x-axis, okay? If we do addition and multiplication, now we get a real number, then it again lies in x-axis, okay? So this x-axis is stable with addition and multiplication. So for instance, I in x is 1 plus 2i. Now this is the 3i. This is again of this form, still lies on the x-axis. So it's closed. Of course, you multiply, for instance, multiply by 3 times 2i. Now again, you get a 6i. 6i is again of this form. Okay, so it's stable under multiplication by scalars and addition or subtraction. So this is actually U is a vector space. So U is a vector space. U is stable under vector, vector addition and scalar multiplication under addition of vectors. Addition or subtraction. Subtraction is a special case of addition. Addition of vectors. And scalar multiplication. Now, if you rescale the x-axis, this is infinity length. You get this infinite length. So you get x-axis. So it's stable. Scalar multiplication. Here you see the x-axis is infinite length. Okay, if it's a finite length, that's not possible. If you multiply a finite length, the length is always changing. So it's not stable under multiplication. So this whole collection is stable. Okay, you multiply infinity with a number, non-zero number, is again infinity. Okay, so it's stable. Now you see this is the one-dimensional line. So this actually we have this is called R1, the space R1. So its structure is R1. So this we essentially R1. Okay, we use the notation equal. Okay, vector space equal to R1. Now if we have two-dimensional space, another space V. Now this is the, for instance, xi plus yj. xy, they are in real numbers. Now this is, a point xy in the plane. So suppose we have point xy, the coordinate xy. Then it corresponding to a point. Okay, a point xy in the xy plane corresponding to, suppose this point P is, so xy, a point in the xy plane corresponding to OP, the vector OP, which is, you see, this is x direction is, this is the xi, and the y direction is yj. This point is y. So this is the xi plus yj. So you see, this correspondence actually tells us this vector space is nothing else, is the xy plane. Okay, it is the xy plane. So it's corresponding to, so this actually, let me get it. This V is corresponding to xy plane, R2, okay, R2, two-dimensional space, xy plane. You can easily check, you add two vectors, xy, again, lies in this plane, okay? For instance, that's very easy to check, trivial almost. xi plus y1j, you add a plus minus, x2 I plus y2 j. Now what you get is x1 plus minus x2 I plus y1 plus minus y2 j. So it's again some multiple of I plus some multiple of j. So it's again lies in V. Of course, you check it by multiplication by any number. So it again lies in this space. So it's stable. It's stable. So if you can check if any V1, V2 lies in this space V, then any lambda V1 plus mu V2 lies in this space V again for any lambda mu real number. Okay, so this is called a linear combination of two vectors. Okay, now you see here, you see a line. We can embed a line into the xy plane. We can embed a line into the xy plane. So the first example, the space U is actually strictly contained in the space V. Okay, in this case, they are both vector space. Then we call U to be a subspace of V. Now, so by definition, U and V, they are both. If U is a space, a vector space, that is contained in a vector space V, in a vector space V, then we see U is a subspace of V. Okay, the above examples you see, the vectors, they are the form I, some multiple of I, some multiple of J, and we give a definition. We can construct the vectors from basic elementary vectors. Okay, so suppose we have a collection of vectors giving a set of vectors. So we have many vectors. So this is the set S equal to V1, etc., Vn. So I forget writing the arrow all the time. Now we may linear combination. We may find linear combinations. We may construct, obtain a vector space. Vector space V to be the spine by S, which is of this form: x1 v1 plus x2 v2, etc., plus xn vn, such that xi all in real numbers. Okay, I equal to 1, etc., all the way to n. Okay, so we use linear combinations of vectors to construct vector space. Okay, for example, I is a set S can be I and J. Okay, I and J. Then the spine of S. Now this linear combinations of I and J, so it's xi plus yj. xy plus yj. Now this actually, you see, this is the xy in real numbers. This is corresponding to R2, okay? The xy plane. Now, of course, there may be redundancy in the generating set S. Okay, for instance, example, S to be I, J, I plus J. Now you see there here any linear combination, any multiple of I plus j, for instance, x1 I plus xy plus z I plus j. So if you distribute, so you get x I plus zi, so it's x plus zi plus y plus zg. So again, it's of the form some multiple of I, some multiple of g. Okay, so we have a redundancy. So it suffices. So we can only it suffices that we use only the first two vectors. Okay, so we have redundancy. Okay, suppose this is S1. So the spine of S1 is the same thing as the spine of S. Here S is ij. So you see the vector I plus j does not contribute to something new. So here the I plus j is redundant. So now it's redundant, so we can just delete it. It does not introduce, it does not, so the redundant vector does not produce something new, new. So deleting all unnecessary vectors, unnecessary or redundant. We can choose a minimum generating set. We can choose a minimum.
Professor, I have a question, please.
Question.
Hello?
Yes.
Yeah, I mean, I don't understand that, the last one. Span S1 is equal to span S. How is this possible? Is there something in dimension?
Dimension, yeah. So,
Yeah.
So you see spine
Yeah, I
S.
don't understand.
Spine S. What is
that,
spine
yeah.
S? Spine S
It's,
is over the form xi plus yj. Okay, this is just the xy plane. The vector space is the xy plane. Okay, ig. So you see any spine uses three vectors.
Okay. I got it.
You see any spine, linear combination of three vectors, ij, I plus j. You can write it as some linear combinations of I and linear combination of j. Okay, so this spine of S1 is clearly contained in spine S. You see?
Thank you.
You see, spine S1 is clearly contained in spine S. So you have something. So S1 has something more. So the spine of, so we know spine S1 is clearly, by this thing we know it's contained in spine S. But S1 has extra vector. We should suppose that it spine S1 should clearly contains spine S, because any spine S, anything spined by vectors S in S should definitely contain in spine S1. So they contain each other, so which means they are the same thing. Does that make sense now?
Yes, thank you, Professor.
Okay. They contain each other. A contains B and B contains A, which means A and B are identical, are the same thing. Okay. We can find a minimum generating set. A minimal generating set. Generating set S. Then the number is unique. Where the number n to be defined as the number of vectors in S. is unique. Width is called the dimension. Width is the dimension. We call it the dimension of the spine, which is the dimension of a space of a spine S. Okay. Now the generating set is far from unique. Different people can choose different choice. Okay, different people can choose different choice. So for example, S1 to be I plus J. This set. Now S2 to be I and J. Then this spine are the same thing. You see the spine S1. So suppose we spine S1. How do we get a spine S1? Xi plus Y I plus J. Now if you distribute Xi plus Yi plus Yj. So you see, if you write the thing is, it's a multiple of I, some multiple plus G, some multiple of G, add them together. So this is clearly in the spine. So this is in the spine of S2, okay? Some linear combination of I and some linear combination of J, okay? So this means spine S1 is a subspace of spine S2. Its content is the space S2, spine of S2. Now, of course, spine S2, spine X2, S2 is Xi plus Yj. Now, you can write it as this form, Xi plus Yi plus J minus I. So you see, this will be, you do some work. So this will be Xi plus Yi plus J minus Y times I. So I combine with I. So this get X minus Y I plus Y times I plus J. So you see, it's a combination of I and I plus J. So this is, by definition, is in the spine of S2. So any vector in the spine S1 also lies in the spine of S2. So this means spine S1 spine S2. This is I confused myself. Spine S2 is also contained in spine S1. Okay, so they mutually contain each other. So which means they are the same. Spine S1 contains spine S2, and the spine S2 contains spine S1. So this means this should be spine the same space. Okay. Any questions? Okay. Example. X, Y, G, X, Y, Z. Now, the example I, K. What does IK spine? What does IK spine? What is the spine of the vector I and of the vector K? What does this IJ spine? What's the vector space spined by I and K?
Is it R3?
I is along the x-axis.
X and
K
Z
is
axis.
along the z-axis. What's the spine of I and K?
A plane?
Yes, it spans the which plane?
XZ.
XZ plane. Yes, correct. XZ plane. XZ plane. IG spans the XY plane. Okay. GK spans the YZ plane. Okay. Okay, example. Determine if the point P 1, 2, 3 is on the spine on the plane. Now to distinct the vectors, we will spine a plane. We'll spine a plane. By the two vectors. Let's see, V1 is this vector 1, 1, 0. And V2 is 0, 1, 1. Okay. So let's see what's the spine of V1 and V2. Now the spine of V1 and V2 is of linear combinations of V1 and V2. So this will be X multiplied 1, 1, 0 plus Y multiplied by 0, Y, 1. So this X multiplied, distribute X inside, so we get X times 1, X plus Y times 0, get a 0, Y times 1, we get a Y. Okay, so add component wise, then you get X plus Y and Y. Okay, so you see a space, a vector that lies in the spine. So it looks like, you see, the second coordinate is the sum of the first and the second, the first and the third. So now you see the point. Okay, you see, then you see P is 1, 2, 3. The spine, you see, the first plus the third, add them together, correspond to you get X plus Y. Okay, so you see 1 plus 3, X plus Y is 4, which differs from the second coordinate. Okay. So you see, we have OP can never be written as XV1 plus YV2. Okay. Can never be written in this form, which means P is not in the spine on the plane, which means P is not on the plane. On the plane. Spined by V1 and V2. Okay. More examples. Example. Suppose we have a unit cube. Let me write down. Let me first write down this equation of a plane. Equation of a plane. Equation of a plane. Okay, now suppose we have a plane. Suppose we have a plane. Okay, now we have the normal direction n. Okay, suppose n is ABC. Okay, we have a vector in the direction of ABC. Now suppose we have a point P. P0. P0 is coordinate x0, y0, z0. Okay. Then how do we determine the plane, equation of the plane? Now suppose we have any point Q. Suppose let Q, x, y, z. X, y, z be a point on the given plane. Given plane. Then we have a vector PQ. Then we have P0Q is perpendicular to the normal vector n. Okay, so this is equivalent. Then we have n dot product with P0Q should be 0. Okay, this is equivalent. This condition is equivalent. Q is on the plane. On the plane. So this is equivalent. Then we can write the dot product equal to 0 as, so we can find P0Q is head minus tail. The coordinate of Q you can write down. X minus the x coordinate of P0. X0, y minus y0, z minus z0. Okay. Now n is, you see, n is A, B, C. Now if you do dot product, n dot product with P0Q, now x dot x multiply x, y multiply y, plus z multiply z, you get a 0. Okay, you get a 0. Okay, so a plane. Now, if you rearrange this, you can get ax plus by, x, y, z. They are variable, cz, and then all the remaining are numbers. X0, y0, z0 multiply abc. They are numbers. We can write it as d, a number d equal to 0. Okay, so this is actually a plane. Okay, a plane that has normal vector in the direction ABC. Okay, in the normal direction ABC. So this is equation of a plane. Equation of a plane. Okay, if you have no z direction, you project to the xy axis. You project onto the xy plane, then you get the a line. Then you get a line. You get a line. Equation of a line in the xy plane. Okay. Any questions about this example? All right, let's study another topic, maps between vector spaces. Okay. Idea. We study the structure of an object. The structure of an object by its relations. By its relations with other objects. So this philosophy was now developed to a branch of mathematics called category theory. Category theory. This is actually the foundation of mathematics. The foundation of mathematics. Now, the foundation of mathematics actually, people first realized the set theory by Cantor. Okay, by Cantor. Then from set theory, now people realize it. Set theory focus on objects. Okay, focus on objects. And then people realize that the relation is more important than objects. Okay, this people's understanding in mathematics actually gradually changed. Okay, so the foundation of mathematics actually also changed from set theory to category theory. Category theory. Okay, for instance, we have functions between, we know, everyone know functions between numbers. Now also we define functions, but now we define functions on vector spaces. Okay. Now we want to study vector space by functions on vector space. We want to study maps, or you can view this as functions between vector spaces. Vector spaces. That, when we should preserve the original structure when we do some maps. We do not want to destroy the structure as a vector space, so that we should preserve the key feature, preserves the vector space structure. Vector space structure. Okay, let's see some examples. Okay, let's see this example. Rotation by power 2. Rotation by 90 degree, power 2. Now, suppose we consider the rotation of this space. We have xy. Okay, xy, this space. Now the vector, this is one here, this corresponds to I, the vector I. Now we have vector G here. Now what happened if we rotate by power 2? If we rotate by power 2, I we write as in column wise 0, 1. The first component 1 means x direction is 1, y direction is 0. Now if we rotate it by power 2, what do we get? When we rotate it, we use this positive direction. Rotated by power 2. What do we get if we rotate I by power 2? And what do we get if we rotate G by power 2? Anyone know? What do we get if we rotate I by power 2?
Do we get 0, 1 for I and 1, 0 for J, negative 1, 0 for J?
So I, what do we get for I if we rotate I by 90 degree?
0, 1.
0, 1, correct. We obtain J equal to 0, 1.
We
Okay.
obtain J.
So I, if we rotate I, then we get J. How about J? We
Take
rotated
K.
J by the power 2.
Negative I.
Negative I, good. Which will be, I will be negative 1, 0. Okay. Now we preserve this operation, rotation by power 2, preserves the vector space structure. Preserves the vector space structure. You know, you see, if we have this vector plus this vector, we rotate, so the addition, so this is V1, V2, we get their addition, V3. Now, if we rotate this thing, then we rotate it by power 2, then this is, we still have a parallelogram, okay? If we rotate this parallelogram, then again, we should again obtain a parallelogram, okay? Rotated it. So the addition law is still preserved. So we still preserve the vector space structure, okay? Addition law is preserved. Is still true, you know. So this is again true. So we preserve the vector space. So scalar, of course, scalar multiplication is again, multiplication is also preserved. Okay. So for instance, a vector, if you make it longer, you know, make it twice longer, and then if you rotate it, now this vector, you get this vector, and then this vector, you get this vector. So the multiplication by a scalar is still preserved. The operation of multiplication by scalar is also respected by this operation. So you see, the vector space structure is again preserved. So this operation preserves the vector space structure. Okay, so now how does the general vector transform? Okay, for instance, if we have xi plus yj, this will transform to, you know, xi will transform to xj, and yj will transform to, you know, j correspond to transform to negative I. Okay, so if we write in this form, x, I we write it as 1, 0, y we write as 0, 1. Then this corresponds to this side we get x 0, 1, and then we get y negative 1, 0. Okay, so this will be x times 0, 1, then we get 0x. This we get negative y 0. Okay, so this we get xy. So this we get negative yx. Okay. Okay, you see, if we rotate it by power 2, the vector xy will correspond to the vector negative yx. Okay. Now we use some objects to represent this operation, the rotation. Now you see, we let A to be this object, 0, 1, and negative 1, 0. Now what is the thing? It's a 2 by 2 matrix. A 2 by 2 matrix. Be a 2 by 2 matrix. So they think we put a bunch of numbers in 13 order. Okay, we call it a matrix. And each component its component is called an entry. An entry. Okay. Now we can locate the entry by the row number and column numbers. Okay. We may locate an entry by its row and column numbers. Row and column numbers. So suppose it's i's row, j's column. Then we see and call it the I and C, the ij's entry. ij's entry. Okay. Now this thing E is an operation that corresponds to the rotation. Okay, correspond to the rotation. Okay. Okay, here, what is the, why do we put A in this form? Why do we put A in this form? So you see the first column, let me just write this A here. Now, remember our rotation, our rotation is, let me write A here. A is what, why do we put these numbers here? Let me copy A here. Now A is, remember X, we may map this I to 0, 1. Now, the first column of A, is exactly the thing. The image, the result corresponds to I, okay? Now, what is J? J is 0, 1. It maps to negative I, which is negative 1, 0. So we put the second column to be exactly the results, the output of J, okay? The output of J. So this operation A, this matrix A contains all the information of this transformer. Does that make sense? Because it determines the result, it tells you the result of I, it tells you the result of J. And any other vector, you can determine it by I and J. Okay? So this matrix A, the matrix A contains all information of this transformer. Contains all information of the transformer, or the rotation by power tool, because it determines I and J, the output of I and J, then it determines all other vectors. Okay. Okay, for any vector I, xi plus yj, the general vectors in this xy plane. Now we determine the output. Okay? Determine the output. Now, determine the output. This will be, remember, I will correspond to J. Now, y, J corresponds to negative I. So you see, if we write anything as x, y, the thing, what we get here is J is 0, 1. Negative I is negative 1, 0. So this corresponds to, the operation is this negative yx. Okay. So now our operation is A. Remember, our operation is A. A is determines the operation. So if we write in this form A x y, then the output should be negative yx. negative x. So you see, if we do it, we replace a by this thing, xy. So this is a. So we see the multiplication should be defined. The output, the result should be defined as, if we define it in this form, 0 times x plus negative 1 times y. 1 times x plus 0 times y. Then this actually exactly is negative yx. Okay, this tells us a rule how to determine the output. Once we have this matrix A, how do we get output by this operation? Okay, for instance, this rule tells us xy get output to be negative yx. Okay, now in general, if we have A as this A, B, C, D, this means, what does this mean? This means if we plug in, this means we plug in I, the output is this vector AC, which is AI plus CG. Now we plug in G, the first column gives the result of output of I. The second column gives us the output of J, okay? So we get the second column, the output of J, which is a BI plus DJ. So you see, then this means what do we get? How do we get AXY? What does this mean? AXY means A output of XI plus YJ. Okay, so this means now linear property, we can distribute AXI plus AYJ. Now the result of I, the output of I correspond to X times AC. Now Y, the output of J correspond to B and D. So this corresponds to linear property. We get AX, CX, scalar multiple, and then multiply Y inside, we get BY, DY. And then add component wise, then we get AX plus BY, CX plus DY. So if we given a matrix A as ABCD, then the output of AXY is AX plus BY, CX plus DY. So this means we should define it to be the rule of multiplication. So we should define it to be this, to make it to be a natural operation. Define it to be this. Okay. Or if you write in this form, or you can write in this form as X times AC plus Y times BD. Okay, a matrix tells you a rule how do you do the transform. Okay, plugging X, what do you get? Plugging Y, what do you get? Okay, the first column tells you what you get for X for this 0, 1. Okay, output. So the output of 0, 1. What's the output corresponding to? If you input of 1, 0, this vector, what do you get? Okay, the second column tells you what do you get for the result. Second column is the output of 0, 1. Okay, 0, 1. Okay. Okay, you can also write in this form. This is dot product. So if you write in this form, then you can write as dot product. So you can also write anything as dot product. You can also write R1 times dot product with U, R2 dot product with U. Here R1 is the first rule with AB. R2 is the second rule, CD. Now U is XY. So this is the first rule vector. The second rule vector. Okay. Let's see some examples. Example. If we input I, output is also I. If we input J, output is also J, then there's nothing changed. Okay, nothing is changed. So then you have Xi plus Yj. Now numbers are fixed. I map to I, J map to J. Is again itself, i.e. any vector is mapped to itself, i.e. any vector is mapped to itself. Nothing changes. Then the matrix, what is the matrix? The image of I is the first column is the image of I. The second column is the image of J. So this is the identity map. This is the identity map. Identity map. You can check. I times any XY. This is a Y1 0 0 times XY. And this you get X coordinate X times the first rule plus Y times the second rule. So you get this is again X 0. The second thing you get a 0Y. So this you get XY. Okay, XY. So you see, this is the identity map. Nothing changes. Okay, the idea of this idea is actually really important. We use matrix as an operation to certain objects. Okay, now here in particular, this rotation by power 2 is invertible. If you rotate it by 90 degrees, you can rotate it back by 90 degrees. Then nothing changes. So it's invertible. Nothing changes. So the idea of is the following. If we have invertible operations on objects, if you play the Rubens cube, it's invertible. Anything transform, you can transform it back. Okay, Rubens cube. So it's invertible operations. Invertible operations on objects. I.e., this gives us a symmetry, certain symmetry of these objects. And then if you study physics, now symmetry plays a really important role in physics. It governs the fundamental rules of the universe. Okay, for instance, the conservation law of energy. For instance, what symmetry of the physics rules? This one, translation invariant, i.e., the physics rules that we use today should be the same thing as the physics rules that we use tomorrow. Okay, it's translation invariant. Okay, translation invariant with respect to time. And then if you assume this fundamental symmetry of the law of nature, then you can prove by mathematics that the energy, the conservation law of energy. If you assume that our physics rule should be the same with respect to translation. For instance, the physics laws that we use at Philadelphia is the same thing as the physics laws that we use at New York. Then from this fundamental rule, and then you can deduce from mathematics that the conservation law of momentum, etc., etc. So symmetry is actually really, really important in not just physics and also in mathematics. And it's a huge branch of mathematics that study symmetry. This is called group theory. Group theory study the symmetry of objects. For instance, if you study chemistry, certain materials, certain atoms, they are symmetric with respect to certain rotation. And this actually is important rule. Group theory plays important role in chemistry, in physics, and of course in mathematics. And you see, we use certain objects, matrices, gives us a natural thing to study this kind of operations. Okay, so this idea is pushed further by mathematicians. So linear algebra is, or you call it matrices. We study matrices. The objects that we studied is matrices and vectors. Now this provides, so you see, as we see from the last example, the objects A comes from an operation, rotation. This kind of language, linear algebra, provides a natural language. To study groups, symmetry, invertible operations, okay, or we call it groups. Groups is just a collection of these invertible operations. Now this thing is called representation theory. We represent certain symmetry by matrix. This is called representation theory. This representation theory was developed at the beginning of the 20th century by the pioneers of this thing. Pioneers are Burnside from the United States and Frobenius from Germany. They competed with each other, neck to neck. Okay, they competed with each other, Frobenius and Burnside. Okay, actually, really important thing in group theory is to find the building blocks of the fundamental symmetries. This is actually one of the most important problem in group theory. Classify all possible symmetries. And this work actually takes 10,000 pages, more than 10,000 pages of papers to work it out. And still there are some people that do not believe the classification of the fundamental symmetry groups. It's another story, okay? Okay, now it's maybe a little further to go that far. Let's go back to this basic idea Okay, composition of operations. When we study functions, we have composition of functions. We have chain rule, blah, blah. But then here we can also have composition of operations. Okay, now we should determine what rules that we should describe the composition of operations. So suppose we have two operations. So this matrix, a matrix gives you a rule how to transform vector space. Okay, you input some vector, you output a certain vector. Okay, so it's transformation. Now, of course, we can compose this kind of operations like what I did for functions. Composition of operations. Okay, suppose we have this operation A is given by AC BD. This tells us that I transform output of I is AC. The first correspond to the first component correspond to AI. The second correspond to CG. Okay, CG. That's CG. Okay, now this corresponds to G, correspond to map it to the second vector, column vector, which is BI plus DG. Okay, now suppose we have another operation B, which is PQRS. This means I map it to PR, which is a PI plus RG. And G map it to QS, which is a QI plus SG. Now, what's the composition? Now, let's do the composition. What is I? We, under this map A, I map it to AC. Okay, map it to AC, which is AI plus CG. Now we plug in this output to B. Then we get, I correspond, the output of I, A is, the linear coefficient does not change. I correspond to the output of I. What is the output of I under the operation of B? The output of I under the operation B is PR. Then the operation of the output of G correspond to QS. So this will be, if you write down, so this will be AP, AR plus CQ, CS. So you see this will be, the output will be added them together component wise. So this will be AP plus CQ, AR plus CS. Okay, so we get this rule, the output. We input I. The output should be AP plus CQ. We copy that again, CQ. AR plus CS. Okay, now if you do this thing for J, let me quickly do it for J. J, now under A, under the mapper of A, then we get BD. You check what A is. Remember, A is ABCD. So the second column is BD. So this is a BI plus DG. But then under the operation of B, now we got a B times the output of I under the operation of B. You see, the image of I under the operation of B is Okay, so here this is B. The I mapped to PR, so it will be I correspond to PR. Now DG, how over the DG? D is G. What's the image of G? What's the image of G? You see G goes to QS. G goes to QS. So if you write this thing again, so it will be BQ BR plus DQ DS. Add them together component wise. BQ plus DQ, sorry, this will be P. And BR plus DS. Okay, so we get, finally we can get, we map a J to under this rule AB composition. We first do A, we then do it for B, okay? Then we get this thing should be BP, let's copy that thing again, BP plus DQ, BR plus DS. So we have I correspond to AP plus CQ, AR plus CS. Okay, so that you see under the rule of composition, so we see the rule BA. We first do A and then do the operation of B. So it's B multiply A. Should be the first column is the input, the output of I. This will be AP plus CQ, AR plus CS. BP plus DQ, BR plus DS. So you see, if we have two matrices, we should define the multiplication. Remember, B is this operation. B is PQRS. A is ABCD. Now you see this is B, this is A. Then we should define it. If we can define an operation on this AB, then a natural operation is actually we define it to be this. Define it to be AP plus CQ, or you put a P there. You put this. Let's put PQ first. PA plus QC, and this is PB plus QD. And then this is RA plus SC, and this is RB plus SD. How does this make sense? How does this make sense? Now, if you see this is the first entry, one entry is nothing else, is the dot product of P. So this is the PQ dot product with AC. So this is the rule column C1 dot, sorry, this is R1 dot C1. So this R1 of B dot product with C1. This is R2 dot, this is the R1 dot C2. This is R2 dot C1. This is R2 dot product with C2. Here, B is rule vectors R1, R2, and A is column vectors C1, C2. Column vectors. With this, you can actually define. So this gives us a natural way to define matrix multiplication. If you view matrix as multiplication operations, then this gives us, a natural definition. How do we compose matrices? Okay, how do we compose matrices? How do we multiply matrices? Okay. We have done a lot today. Maybe let me stop here. And then try to do some homework. I will post the homework problems and practice about this kind of idea. How do we multiply matrix? Okay. How do we use operations? Use matrix to do operations.
Professor, I have a question, please.
Yes.
So what will the project look like? Could you give us a sample about the project or some information about it?
The project. Right now, I don't have any project yet, but I have certain candidate like doing. I will give you some example at the end, at the proper time to give you the project. Right now, it's too early to talk about the project because we haven't done yet. We haven't done the fundamental thing yet, like a matrix multiplication. So later we will, at the proper time, I will assign certain project.
Okay, thank you.
Uh-huh.